Hope you're doing well. This is going to be my lab 4 presentation on bar magnets. So let's get right into it. So the experiment here is pretty straightforward. What we're doing is we're measuring the distance dependence of the magnetic field due to a small bar magnet, and we're comparing our measurements to the distance dependence that was predicted by equations for the on and off magnetic fields. And we're deriving this from Biot-Savart law that we did in class. We're going to compare, basically we're going to have one experimental model, which is we're just doing the actual experiment, and we're going to use our equations in a computational model that we make using ClosScript, and we're just going to compare the values. That's pretty straightforward, right? Let's get into it. Before the experiment, let's just get into some preliminary results. As expected, the distance from the magnet increases and the magnetic field decreases. The magnetic field of a point on the parallel axis of the magnet will be twice as strong as on the perpendicular one. So these are the basic results, and we do have some differences between our experimental value and our computational value. As you can see here, the values I've listed here, these are all from the experiment itself. So n equals minus 2.6758, k equals 8.382 times 10 to the power minus 7, mu equals 3.8837. These are found from our experiment. So these are the physics principles that sort of drive this experiment, right? Oops, my bad. We model our magnetic field versus distance. We use the on-axis B field formula, and we use the Biot-Savart law. All of these are sort of listed here. The equations that I'm using, this is our modeling of the distance. This is the on-axis B field. This is the Biot-Savart law. Our system is just our phone and the magnetometer. Our surroundings are just the Earth and bar magnet and the bar magnet. So the actual experiment is it's a little bit lengthy. First, we place the bar magnet at one end of the meter stick, an east-west meter stick. Axis is a long centimeter stick. And so we place the phone a few centimeters away from the magnet, and then we slide it down a line that's perpendicular to the meter stick. What we do is we find where the x component absolute value is at its maximum and the y component value is at its absolute minimum. We rotate the smartphone and then we do this again, right? We rotate 90 degrees and do this again. And this time what we're looking for is where the y component is at its maximum and the x component is at its minimum, right? As a result of that, what we then do is that we stick 2 pieces of tape onto the smartphone, one for each position. So once we're done with 3 and we find that position, we're going to stick a piece of tape across the width of the smartphone, and we do experiment 4 and we find where the y component is at its maximum and the x component is at its minimum. We stick a piece of tape across the height of the phone. And basically the purpose of this is that the magnetometer field is where the two upper edges intersect for this field, for this phone, right? Once we're done with that, now we can get into the meat of the experiment. We check the value of the y component into our spreadsheet. We mark the on-axis with tape on the phone itself, and then we just do the same as we did for our on-axis field to find a distance dperp where b net is 100, where b net equals this value, and we record that value, that distance basically. And we then move the sensor a distance from the magnet and determine the x component, y component, and z component here. We correct the prior y component, and we calculate the value of b net, and we repeat this experiment twice more, finding the average with a different distance value each time. So we move the sensor a different distance value each time, determine the x, y, z there, and we find the average, right? So that's what we're doing in the experiment. Ultimately, our results are fairly straightforward. The x component increases as the magnetometer moves closer to the bar magnet. The x component can approximate to 0 when the magnetometer is a large distance from the magnet. And we found our mu to be 3.8837. That's the value I've already told you. This is sort of the spreadsheet that they gave us, sort of plugged in with the results. Here you can see the graph. I apologize for the quality, but yeah, this is sort of what that would look like. Okay, here's our ClosScript code basically for our computational model. And again, this is pretty straightforward. Here we're just creating the magnet at the origin, and this is our function to define the dipole p. Here we have some pretty basic formulas plugged in to find that value. Here we're just visualizing the magnetic field, so we're sort of making the arrows, etc., etc. And again, here we're just defining our observational locations and drawing arrows. Basically, we're implementing our dipole function that we coded previously. And this is the result that we get. And there is a bit of a difference between our experimental value and our computational value, and I'll get into why that is on the next slide. There's just 3 pretty straightforward sources of error: inconsistencies in measurement from like human error, just generally. There could be electronic interference from other sources in the lab because a lot of people were doing the experiment at the same time. Or we could just have inaccurate movement of the phone because we're human beings, right? We might move it a bit to the left or a bit to the right, and that could mess up the experiment. Now to the discussion questions. If we hadn't oriented our experiment to compensate for magnetic north and instead just laid out the meter stick at some intermediate angle, the results would change in the x component. And this would lead to an even bigger difference between our experiment and computational. So it's probably a good thing that we did that. And if we struck two identical magnets together, it's likely that the magnitude would double, but the direction would stay the same. And this is because of superposition, basically, because we're not changing anything else. We're just doubling the power of the magnetic field. We're sticking two identical magnets together. And so in the end, the results will be pretty similar with just the value doubled, right? And so thank you very much for watching. I hope this was helpful.